as we continue our discussion of chemical kinetics, it's going to be important to note that rates can change over time. One of the best ways to see this and to determine rates is by actually plotting concentration versus time. So we have a graph here. We've got a graph representing the reaction of hydrogen with iodine to produce hydrogen iodide. And we've got two curves. The green curve here is representing how the hydrogen's concentration changes over time. Now, if we notice with that green curve that the hydrogen concentration starts out close to 1, and over time it's decreasing. Over time it starts to approach 0. So we're asked first of all if this makes sense. And hopefully it does, because H2 is a reactant. Reactants are getting used over time. Now our other curve, the red curve, is representing what's happening to the the hydrogen iodide. The hydrogen iodide is our product. Now that product is starting out at a concentration of 0, and its concentration is increasing over time. So again, we're asked if that makes sense. And hopefully it should, because our products are always going to be formed in a chemical reaction. And if they're formed, that means they are increasing over time. And so we're seeing that represented here in this graph. Now, if we look again at the green curve, which is our bottom curve, looking at the hydrogen curve, we're asked, what do we notice happens to the slope over time? So if we look closer to where we start, when we're close to that concentration of 1, we've got somewhat of a steep slope. But as we reach closer to a concentration of 0, that line starts to level out a little bit more. It gets flatter. And as that line's getting flatter, that means my slope is decreasing. So over time, our slope decreases. But at the same time, we've got our hydrogen iodide. Looking at its beginning, again, we've got a fairly steep slope there. Over time, it starts to curve a little bit more. It starts to move towards being a little bit more flat. So again, we're seeing that slope decreases over time. So if we recall from math class that our slope is our change in y over our change in x. If we look at this particular curve, our x, or what's on our x-axis, is time. What's on our y-axis is going to be concentration. So based on this, we're asked what two variables are used here to calculate slope. We're then asked to write them in an equation format. So what we need to calculate slope is time, so our x, and concentration, our y. So if we write this in equation form, the slope will equal the change in our concentration over the change in time, because we're looking at the change in y, which is our concentration, divided by the change in x, which is our time. Now, we've just been talking about changes in concentration over changes in time, and we said those were defined as being rate. So that means that the slopes in these graphs indicate rate. But we just talked about the fact that the slopes on these curves are changing. And so rate will change over time. So we're asked what seems to happen to the reaction rate. So not only does it change, but in both scenarios, we said that the slopes were decreasing. If the slopes are decreasing, the rate is decreasing. So in general, we're going to find that rate decreases over time. Now, one of the reasons for this, if we think about, again, those things that impact the rate of our reaction, we said the primary factor was going to be concentration. Over time, we have less reactants available. If my reactants become less available, they're going to get used up slower because we're going to have slower collisions. They're also going to form products more slowly because, again, we have less collisions. There are less reactant particles to collide, resulting in lower rates. So we've got a graph here of concentration versus time. From these types of graphs, we can determine 3 types of rates. The first type of rate we can determine is an instantaneous rate. This is the rate at a particular instant in time. It's determined by taking the slope of the line tangent to the point of interest. So we're not actually using the slope of the curve. What we're doing is we're finding the time that we're interested in on our graph. We draw a tangent line to that point. So we've got to recall from math class what tangent lines are. Tangent lines should touch the curve only at that given point. They should be drawn such that the angles between the line and the curve on each side of the point should be the same. Once we've drawn that appropriate tangent line, we're going to calculate the slope. When we calculate that slope, we're picking 2 points on the tangent line. So again, not on the curve, on the tangent line itself. And when we do so, this might be a little bit different from your math class. Normally, you might be able to pick any points. But because we're worrying about measured data and significant figures, we want to pick points as far apart as possible in order to minimize the loss of significant figures. So, this is the graph we'd already looked at with the hydrogen and the hydrogen iodide. This particular graph, again, or what we see, we actually see some calculations on this graph. It's showing using the curves to find the rate of hydrogen disappearance at 50 seconds into the reaction, as well as the rate of hydrogen iodide at 50 seconds into the reaction. And so this is actually showing that calculation. So if I look at my hydrogen curve, if we were to determine our rate for the hydrogen, we're going to come to our curve and we're going to come to 50 seconds. So again, we're looking at the disappearance at 50 seconds. And I've got my point. We're drawing a line tangent to that point. So that black line that we see, that is our tangent line. And so what we're seeing done is the slope being calculated of that tangent line. Now, ideally, we would actually want to draw this slope or this line out a bit further so we can get points further apart. But again, notice it only touches my curve at that point. And here, the angle here versus the angle here are the same. And then to calculate the slope, they're taking the points at the end of the lines. So we're getting our change in concentration over our change in time. So we're looking at our final concentration on that line of 0.22 approximately. And that's at 70 seconds. And then we're looking at 30 seconds. And a concentration of about 0.5 molar. So taking our change in concentration over our change in time, again, using the points on the line, that's where we're getting that 0.28 molar and our 40 seconds. Now, on the graph, they have it indicated as negative 0.28, but remember, our rates are positive, so we're taking the absolute values. So taking the absolute value of the change in concentration over the change in time gives me a concentration of 0.007 molarity per second in reference to my hydrogen. Now they're doing the same thing with the hydrogen iodide. At that same point in time, at 50 seconds, so right here, they've drawn the tangent line. So again, we're seeing that equal distance. So an equal distance from the point, the angles are the same. They're using the end of the line as the 2 points to calculate the slope. So here, calculating the slope of that tangent line, we're going to get 0.014 molarity per second. The next type of rate we can determine from graphs of concentration versus time is an average rate. The average rate is the average of the rates over a particular time period. So it's over a range of time. It's determined by taking the slope of the line connecting the 2 points on the curve. So the difference, instantaneous, we use points on the tangent, not on the curve. Here we're using the specific points on the curve. So say we want to know the average rate of hydrogen formation between 50 and 70 seconds. What we would do is we would go to our curve and we would find 50 seconds. So it's going to be right here. And we're going to find 70 seconds, which is going to be right here. We're not on that tangent line anymore. We're on the curve itself, which puts us at different concentrations. And so from those molarities and concentrations, we're taking our change in hydrogen between those 2 points, divided by the change in time at those 2 points, and we're calculating the rate. And we get a rate of 0.006 molarity per second. So again, it's the slope between the 2 points in time we are interested in. So if we were interested in the rate between 0 and 20 seconds, we would then go to those 2 points on the curve and calculate the slope. Now, the final type of rate that we do have is an initial rate. The initial rate is the rate at the beginning of our reaction. It's a special type of instantaneous rate. So it's the rate at a time of 0. So we would calculate the initial rate the same way we would any other instantaneous rate. We would draw a tangent line. So based on what we just talked about, again, there are 3 rates that we can determine from a concentration versus time graph. We have instantaneous rates. We have average rates, and we have initial rates. Now, we saw with the calculation of the hydrogen's formation at 50 seconds and the hydrogen iodide's formation at 50 seconds, we got different values for those. So we're asked again, why would these be different? So that goes back to the balanced chemical equation. For every 1 hydrogen I use, I form 2 hydrogen iodides. So their moles are changing at a different rate. And this is because, again, they've got those different mole ratios. Now remember that our materials in a given chemical reaction are related through the coefficients in the balanced equation. So if I know the rate for one substance, I can determine the rate for any other substance without going back to my graph. So that's what we're asked to do here in this problem. So using the rate that we already determined for the hydrogen, which we said was going to be 0.006 molarity per second, which is moles of hydrogen per liter per second. We're going to take that and we're going to use that to convert to the rate for the hydrogen iodide. So looking back to our balanced equation that we had previously, it's 1 mole of hydrogen for every 2 moles of hydrogen iodide, which will give us a rate double that of the hydrogen. So we see a rate of 0.12 molarity per second for the hydrogen iodide. So with this material, we need to be able to take graphs and determine any of our rate types. So we need to be able to determine average, instantaneous, and initial rates. We also need to be able to take our balanced chemical equations and convert from one rate to another. So here we've got a graph. We've got the reaction of hydrogen with bromine to produce hydrogen bromide. So in this particular scenario, we could have measured the bromine, and we are charting the change in bromine's concentration over time. And we're asked to use this graph to calculate, first of all, the average rate of the reaction between 10 and 20 seconds. So what we're going to do is we're going to come to our graph. We're going to locate 10 seconds. We're going to locate that on our curve. And then we're going to locate 20 seconds. We're going to find the slope between those. So we're looking at the change in the bromine concentration over the change in time. So that's going to be my final concentration, which is about 0.8 molar, minus my initial, which is at about 0.9 molar. And that's going to be divided by my change in time, which was 20 seconds minus the 10 seconds. And again, we're taking absolute values. And we'll end up with a rate of 0.01 molarity per second in relation to our bromine. So again, the average rate, we take the 2 points in time we're interested in, we go to the curve, we identify the molarities and time at those points, we calculate the slope. For B, we're asked for the instantaneous rate. So that instantaneous rate, we're on instantaneous rate at 50 seconds. So we locate 50 seconds. We're going to draw a tangent line. Let me pick this point. And we're going to calculate the slope between those points. So we would be looking at, so we've got 70 seconds and 20 seconds. My concentration at 70 is at about, let's say about 0.42. My concentration at 20 seconds is about 0.75. We take the absolute value. Again, this particular graph isn't so great. My tangent line's not so great. Again, you would have ruler and paper to use in order to draw those tangent lines, pick your points, calculate the slope between them. We should be getting a slope of approximately 0.008 molarity per second in reference to the bromine. They may be off slightly depending on the points we picked or how much we estimated, because again, we don't have great significant figures with this particular graph. Now, finally, we're asked for the instantaneous rate of the formation of HBr at 50 seconds. I have no HBr information on my graph. What I just determined, though, was bromine's rates at 50 seconds. So we're going to take the 0.008 moles of bromine per liter per second. We're going to convert that to moles of HBr. Looking at our balanced equation, it's 2 moles of HBr over 1 mole of bromine, which will give me a rate of 0.016 molarity per second in regards to my bromine. So again, we're seeing twice the rate, and we would expect twice the rate because for every 1 bromine I use, I'm forming double that amount of my hydrogen bromide. So graphs are one way we can determine rates. We can look at concentration over time, we can get instantaneous rates, average rates, and initial rates.